Yay. Hi, Sophie. Right. So, like I said, we're going to move on today. We are moving on to organic chemistry, which is fun. Best thing ever. It's the best part of chemistry. That is topic 6, I believe it starts from. Yeah? So, hopefully. Go. Perfect. Organic chemistry. So this will now take me until the end of the course, the end of the Year 12 course, to finish all of the organic that we need to do. Okay? It is crazy, but it's also very good. Okay, so you know, hopefully you already know lots of things about organic chemistry anyway from GCSE. So let's start. You tell me what you know already. Okay, alkenes and alkanes. We know about those, hopefully. Thank you, Jemima. Okay, so organic is basically the study of the chemistry of carbon. Okay, it has nothing to do with organic farming. Okay, if someone tells you that the food is organic, well, that's obvious anyway. Food is organic. It's all got carbon in it. Yeah, nothing to do with how it's grown. Go on, Ziad.
Are hydrocarbons part of organic chemistry?
Exactly, hydrocarbons are part of organic chemistry. Okay, so that's possibly the biggest part. I mean, most organic compounds will. Obviously, they all contain carbon, they have to, but they will also have a lot of hydrogen as well. Doesn't mean they are all called hydrocarbons, but almost always an organic compound will have at least a few atoms of hydrogen in it. It could also have oxygen, probably the next most popular element to go with that. Okay, so carbon, hydrogen, oxygen. We may have nitrogen. We may also have sulfur as well. Okay, but those are really the elements that we're thinking of. Okay, most of what you are made up of as organic people is carbon, hydrogen, oxygen, and nitrogen, and little tiny bits in between. Okay, like I say, little bits of sulfur, a little bit of phosphorus. Okay, and most of that will make up your body. Yeah, and yet there's millions of different compounds, all because carbon is so exciting. Yeah, look at the excitement on my face when I say carbon, organic chemistry. Yeah, it's amazing. I'm going to try not to repeat everything from GCSE because it gets a bit boring if I do that. But we're going to start off nice and simply with types of formula. Okay, you already know a little bit about this. Okay, you already know one type of formula when we did topic 5. What did we have to actually calculate quite a lot of in topic 5? What type of formula? Empirical formula. Okay, so Yulia, you know, what's the definition of an empirical formula?
The simplest ratio of the elements in the compound.
Exactly, the simplest ratio of elements in a compound. That is an empirical formula. Good. Let's start it off then. So, empirical formula. We'll define all of these for you. Here we go. So, definition, empirical formula, simplest ratio of elements in a compound. If I go one level up from that, make it a tiny bit more complex, okay, then we're going to have the molecular formula. What do I mean, do you think, by the molecular formula? What's that, the definition of that? Ziad?
It's the actual compound with the loading thickness form.
So it's the actual number of atoms in the compound, okay? Not in its simplest form, but the actual number that you'll find, okay? So, the actual number of atoms of each element in a compound. Okay, so we may as well just work with a couple of examples of that, I guess. And we'll try and make them organic. So, maybe you'd be able to tell me butene. That's a good one. Can anyone actually use a bit of their knowledge from GCSE Chem to tell me what the molecular formula of butene might be? How many carbons has it got for a start?
4, yeah.
4. Okay, yeah, it's 4. Lots of you are already saying 4. So it goes meth, eth, prop, but. Okay, and then pent and hex and so on. Okay, so it's definitely got 4 carbons. But I guess the tough bit is then how many hydrogens it's got. It's got that ene suffix on it, which means it's an alkene, obviously. Or not so obviously. Ziad? 8. It is, okay? If you remember, the general formula for an alkene is twice as many hydrogens as there are carbons. So C4H8. I'm thinking that's a bit of an odd angle for the iPad, looking at that. I wonder if I can move it so we get a better angle. Okay. All right, so we got to butene being C4H8. Which one of those is that? That's the molecular formula. Okay. If I change that to be empirical, what would that be? CH2. Okay, and you can do that. You could do that with lots of things, couldn't you? What could I do next? What if I had butane? What would the molecular formula be? C4H10, exactly. And the empirical? Someone else? James? C2H5. Perfect. Okay. You kind of knew this already. I'm not going to labour the point all afternoon because that might get a little bit boring. However, we need different ways of showing this now in organic chemistry. And we'll stick with those same examples for a moment, okay? We want to go on to look at what we call displayed formula. Displayed formula is where you show a diagram with all of the bonds. So, diagram that shows all of the bonds in a molecule. If I was going to do butane, let's do butane first, then I'd show a chain of 4 carbons, like that, and then add in my sticks for all of the bonds to all 10 hydrogens. Like that. Okay, that's the displayed formula for butane. What I want you to do, you should be able to do this. Can you come up with how you would draw the displayed formula for butene? Following me now. There you go. You got it? Everyone only wants to whisper now that the iPad is on, don't they?
Just saying that the camera isn't tracking you anymore.
I turned it off for a minute. So it's just it is a bit. Okay, so you got the idea for butene. I wonder actually if anyone came up with some slightly different answers. But butene, we had 4 carbons again. If I join them up in their chain, one of them needs to be a double bond. I'm going to put one there. 1, 2, 3 around this. One there, and 3 on that last one. Okay. Again, displayed formula shows all of the bonds. This time it's an alkene. We've got a double bond there. Did anyone come up with a slightly different version of that? Does anyone look a little bit different? Me? Okay, you put the double bond on the end instead. Okay. Some of you might have put it on that end as well. Okay. We're going to come back to this because this displays another property of organic compounds, which is really, really important. You would have hopefully learned it in GCSE Chem, but you've probably forgotten by now. Okay. And it's next lesson. It wasn't necessarily going to be this lesson. Okay. But it's called, if you remember, isomerism. Yeah. Yeah, ringing a few bells somewhere. Okay. We've still got different ways we can show this. Okay. Some of these I really like. Turn the tracking back on for a minute. Tracking on. Good. So, new definition there. A structural formula, folks, is a formula that shows groups of atoms but still gives the overall structure of the molecule. Now, I find this one a little bit frustrating personally, okay, because there is no perfect rule for you to kind of write your own structural formula. And in fact, exam questions never ask you really to write a structural formula necessarily. But they are given in the information in exam questions. So you need to be able to recognize what it is that you're actually looking at. Okay? So if I was just going to do a structural formula for butane, it would actually be quite easy. I would show CH3, CH2, CH2, CH3. Okay? And I can draw it, I can do little sticks in between, or I can leave them out completely. Okay? Either way would show a structural formula. I know by looking at this that this must be butane. CH3, CH2, CH2, CH3, and it's broken each one of those into a little group. Okay? CH3, CH2, CH2, CH3. Yes, go on.
So what's the difference between a condensed formula and a structural formula, other than the lines connecting?
I wouldn't worry about the difference. I know my poster shows it there. A condensed formula or a structural formula. The condensed formula doesn't have the lines. That's really it. That's the only difference. Okay? And I wouldn't say draw a condensed formula or draw a structural formula. Okay? I'm really showing you this so that you understand it when you read it, not so that you can draw your own. Okay? And if you were asked to draw your own, they wouldn't worry if you put the sticks in. Okay? Most of the time, okay, you may be asked to draw displayed formula with all the bonds, but even then, they would allow you to do this and still give you the mark. Okay? The only one where they really penalise you because you have to do it properly is the next one I'm going to show you. Okay? Which are skeletal formulas. Skeletal formula are awesome. Simplest way to show really complicated molecules. So, defining it is quite difficult with skeletal formula, but it just shows the carbon chain with lines, which sounds really silly until you start to see it. Seeing is believing, okay? Because I can draw butane as a skeletal formula. It looks like that. That's it. I can draw that, and I know that that is butane. You're a little bit like, how do you know that, sir? It's 3 lines. How on earth can you know that that is butane? Because you've got to use your imagination for it a little bit. Okay? On the skeletal formula, each end of the line represents a carbon atom. You don't need to put the circles in there, I'm just trying to represent it for you. Okay? And the assumption is, unless the skeletal formula shows otherwise, everything is bonded to hydrogen as much as possible. So this one would need 3, this one would need 2, this would also need 2, and this would need 3. Okay, so it shows you you've got 1, 2, 3, 4 carbon atoms. So that is butane. Good question. How is it for alkenes? I was just about to show you. Okay, I can do the same again. My 3 lines. But this time, to show that it's an alkene, I can put a double line to show that it is a double bond.
Wouldn't that count as 2 more carbons? Because it's an end of line. Or is it connected?
It's the same line.
Oh, okay.
Essentially, I don't even need the bit on the end. It's all part of the same line. It's just a double line to that. Okay? So that's a double bond. And so the assumption is that, yes, we've got 1, 2, 3, 4 carbon atoms. There needs to be 3 here. There only needs to be 1 here and 1 here. And then there needs to be 3 there. So everything, again, is full up of hydrogen. Okay? So that is butene. Yes, Ahmed?
So they ask us like an example to draw.
Absolutely. So in exams, you are asked to draw skeletal formula. And they're actually really cool. They're the best way to show organic compounds. I love them. Yeah? Because they can start to look like really interesting shapes. Okay? You might also see ones, well, you will also see ones that look like this. 1, 2, 3, little line. So, this one, have a little look up again. Angie, you going to look? Another skeletal formula. Okay? But this shows, so 1, 2, 3 carbons. And it's got this little kind of tiny line on the end. Okay? That doesn't show a join to another carbon. That, if we've got a little line, it shows a join to a different group that it is not carbon or hydrogen. Okay, we need to show it if it's not carbon or hydrogen. Okay, so this is 1, 2, 3 carbons with a little OH group at the end. Does anyone remember from GCSE what kind of compounds have this OH group? Alcohols, exactly. Well done. Okay, so that is, oh wow. If it's got 1, 2, 3 carbon atoms, what kind of alcohol is that? Meth, eth, bismuth, propanol, exactly. Okay, very good. Propanol. So it's meth, eth, prop. So that would be propanol. Very good. I'll just draw in the little dots so you can see where the carbons are. You won't see dots when you draw them, but it helps you just to visualize it first. Here we go, propanol. Perfect. So, little task coming up for you now. Okay, what can I do? Okay, so what I want you to do, 4 examples there. What I want you to try and work out, you can do it either way. You might want to try and draw a displayed formula for each one to show all of the bonds, all of the carbons and the hydrogens, and whatever else there might be. Okay? And then you might want to give the molecular formula as well. Okay?
The second one is like an intersection between all 3.
There is an intersection between 3, yeah, exactly.
So, what would we do in that case?
Well, didn't I say that at each point there'll be a carbon? So, and there.
Okay, that would be okay.
Yeah? See what you can come up with.
So the one percent is double bond, which is in there.
Not necessarily a double bond. I wouldn't have said that. Maybe rather than thinking about it being a double bond, you want to think about how many carbons it's actually attached to.
3.
Right.
Oh, 3.
That doesn't make it a single or a double bond necessarily, but it's how many carbons that carbon is attached to. Okay? All right then, so we've spent some time having a look at that. Hopefully you've got answers by now. Just pop that tracking on. Yeah, good. Let's see what we actually came up with. So the first one should be quite easy. It's just a chain of how many carbons? 5. Yeah? So you should come up with displayed formula, a nice straight line, 5 carbons. We've got H's, H's, H's. See, that's the only frustration about having to do full displayed formula all the time, is how many hydrogens you end up having to put in. And then eventually your H's look like ridiculous things. Okay? But what's the molecular formula for this? C5H12. Good. Did anyone come up with a name for it? Pentane. You didn't have to do that, but people do, because you're just so diligent in what you do. Number 2. Interesting looking one, and it causes a bit of confusion, doesn't it? Okay? But like I said, as you were partway through doing this, if you imagine you can just draw the carbon, okay, at each of those intersections and at the end of each line, okay, and you'll find you get 1, 2, and then 3 carbons. The next that third carbon is joined to 2 other carbons. Okay, so we need to go like this. Okay, and that will show, basically it shows a branch on our chain. Then I put in all of the hydrogens, making sure that everything, all the carbons have got 4 bonds. Okay, there we go. What was the molecular formula for this? Huh? The same. The same as what? C5H12, okay. So again, we've come across this idea, maybe in a little bit more detail now, of isomerism. Isomers, or at least one type of isomer, has different molecules or different structures that have the same molecular formula. Okay, this is a different molecule to this, and yet it has exactly the same molecular formula. Okay, if I was going to give this a name, we've still got a lesson to do on how we name organic compounds, but just to give you an idea, this is called methyl butane.
So it's not pentane.
It's not pentane anymore. It has a completely different name. It's a completely different molecule. So it's called methyl butane.
Because of the branch, the one that's methyl.
Okay. What you do, again, I've still got this lesson to do, but I'll tell you anyway. Ladies, you're going to be with me? If you're going to name a molecule that's got a branch on it, we look for the longest chain first. Okay, the longest chain I can make in any direction is 1, 2, 3, 4. And even if I go in the other direction, 1, 2, 3, 4. So the main part of the name is going to be for 4 carbons, butane. And then it's got this little branch on it that is just 1 long. So it's methyl butane. Okay. Number 3 is a good one. Nice hexagon shape. Take that off. So, 6 in a hexagon, isn't there? So if I put my carbons together in a chain of 6, or sorry, a ring of 6, then how many hydrogens does each carbon now need to join to? Just 2, okay? Because each carbon has 2 bonds at the moment, so it's going to need 2 more hydrogens. Here we go, hydrogen. And how many is that altogether? What is its molecular formula? C6H12, okay. I wonder if anyone came up with a name for it. It does have hexane in it because it's got 6 carbons, but when it goes into a ring like this, we call it cyclo, because it's in like a cycle. Okay, so it is cyclohexane. Huh? You've done it in bio?
Something like that. I'm not seeing it.
You've probably seen something. Glucose looks very similar to that, to be fair. Looks like a ring of 6, but it's got an oxygen in the middle. Okay. And last one? Yes, yeah, sorry. Would they react the same way? Pretty much they would actually react the same way, but they would have different physical properties. They would have different boiling points, melting points, and so on. Okay, that would be the main difference. They'd probably have different densities, but because they are both alkanes, they pretty much react in the same way. Yeah, it's a good question. Last one, number 4. How many carbons did it have? 3. So we want 3 in our chain. And you may have noticed the middle one was attached to a chlorine. There we go. Okay. 3 carbons there, 3 carbons there. I also need, 3 hydrogens there and 3 hydrogens there. I also need a hydrogen there to fill up all of the bonds. Okay. So what would the molecular formula of this be? Exactly, C3, H7, Cl. Okay. What about giving it a name? I'm not going to go into you because I already told you exactly what the name would be. But, well, part of the name comes from the number of carbons. So, if it's got 3, propane. It needs to have propane in the name. Okay? Someone say try. They did, didn't they? Yeah. That's okay. It's fine. We get used to it. So propane. But we need to have this. And, go on.
That's actually a question.
Go on, question, yeah.
So, I think like there's something to do with like if it's on the second carbon, then you say 2 chlorine, like propane 2 and dash 2 chlorine.
Exactly. Okay, so again, I really only wanted to show you about formula today, but it branches off into all types of different things. We've touched on isomerism, which we'll look at again next lesson, but also we're now starting to think how we name compounds nicely. Okay, so this, it has got a single chlorine atom on it, so we would call it chloropropane. Okay, but we need to distinguish as well, because you could have this chlorine in the middle, you could also have the chlorine on the end, like that. Okay, and they'd be two different compounds, very slightly different from each other. Okay, now this is on, no matter which way you look, it's on the second carbon atom. So we call it 2-chloropropane. Okay, and now we've got to a point where we are able to draw fully displayed formula. We can kind of understand skeletal formula. Okay, and we've started already to think about isomerism and the naming of compounds, which has this really ridiculous word, by the way, naming compounds, nomenclature. Yeah? Not really sure why we call it that, but that's exactly what it is. Yeah? Right. 5 past. We're pretty much done.